Appendix 1, Proofs in Mathematics. Proofs are to mathematics what calligraphy is to poetry. Mathematical works do consist of proofs just as poems do consist of characters. Vladimir Arnold. Introduction. In classes 9, 10 and 11 we have learned about the concepts of a statement, compound statement, negations, converse and contrapositive of a statement, axioms, conjectures, theorems and deductive reasoning. Here we will discuss various methods of proving mathematical propositions. What is a proof? Proof of a mathematical statement consists of sequence of statements, each statement being justified with a definition or an axiom or a proposition that is previously established by the method of deduction using only the allowed logical rules. Thus, each proof is a chain of deductive arguments, each of which has its premises and conclusions. Many a times we prove a proposition directly from what is given in the proposition, but sometimes it is easier to prove an equivalent proposition rather than proving the proposition itself. This leads to two ways of proving a proposition, directly or indirectly, and the proofs obtained are called direct proof and indirect proof. And further, each has three different ways of proving, which is discussed below. Direct proof. It is the proof of a proposition in which we directly start the proof with what is given in the proposition. 1. A straightforward approach. It is a chain of argument which leads directly from what is given or assumed, what is the help of axioms, definitions, or already proved theorems, to what is to be proved using rules of logic. Consider the following example. Example 1. Show that if x squared minus 5x plus 6 equal to 0, then x equal to 3 and x equal to 2. Solution. X squared minus 5x plus 6 equal to 0 given. X minus 3, x minus 2 equal to 0. Replacing an expression by an equal or equivalent expression. X minus 3 equal to 0 or x minus 2 equal to 0 from the established theorem AB equal to 0, either A equal to 0 or B equal to 0 for AB in R. X minus 3 plus 3 equal to 0 plus 3 or x minus 2 plus 2 equal to 0 plus 2. Adding equal quantities on either side of the equation does not alter the nature of the equations. X plus 0 equal to 3 or x plus 0 equal to 2 using the identity property of integers under addition. X equal to 3 or x equal to 2 using the identity property of integers under additions. Hence, x squared minus 5x plus 6 equal to 0 implies x equal to 3 or x equal to 2. Explanation. Let P be the given statement x squared minus 5x plus 6 equal to 0 and Q be the conclusion statement x equal to 3 or x equal to 2. From the statement B, we deduced the statement R, that is x minus 3, x minus 2 equal to 0 by replacing the expression x squared minus 5x plus 6 in the statement P by another expression x minus 3 of x minus 2, which is equal to x square minus 5x plus 6. There arise two questions. One, how does the expression x minus 3 of x minus 2 is equal to the expression x square minus 5x plus 6? 2. How can we replace an expression with another expression which is equal to the former? The first one is proved in earlier classes by factorization, that is x square minus 5x plus 6 equal to x square minus 3x minus 2x plus 6 equal to x of x minus 3 minus 2 of x minus 3, that is x minus 3 of x minus 2. The second one is by valid form of argumentations, rules of logic. Next, this statement R becomes premises or given and deduce the statement is x minus 3 equal to 0 or x minus 2 equal to 0 and the reasons are given in the bracket. This process continues till we reach the conclusion. The symbolic equivalent of the argument is to prove by deduction that P implies Q is true. Starting with P, we deduce P implies R implies S implies dot 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 implies Q. This implies that P implies Q is true. Example 2. Prove the function f, that is R to R, defined by fx equal to 2x plus 5 is 1 1. Solution. Note that a function f is 1 1 if fx1 equal to fx2 implies x1 equal to x2. Definition of 1 1 function. Now given that fx1 equal to fx2, that is 2x1 plus 5 equal to 2x2 plus 5 implies that 2x1 plus 5 minus 5 equal to 2x2 plus 5 minus 5, adding the same quantity on both sides. That is 2x1 plus 0 equal to 2x2 plus 0, 2x1 equal to 2x2. Using additive identity of real number, 2 by 2x1 equal to 2 by 2x2 dividing by the same non-zero quantity, x1 equal to x2. Hence the given function is 1 1. 2. Mathematical induction. Mathematical induction is a strategy of proving a proposition which is deductive in nature. The whole basis of proof of this method depends on the following axiom. For a given subset S of n, if 1. The natural number 1 belongs to S and 2. The natural number k plus 1 belongs to S. Whenever k belongs to S, then S equal to n. According to the principle of mathematical induction, if a statement Sn is true for n equal to 1 or for some starting point j, and if Sn is true for n equal to k, implies that Sn is true for n equal to k plus 1, whatever integer k greater than equal to j may be. Then the statement is true for any positive integer n for all n greater than equal to j. We now consider some examples. Examples 3 show that if A equal to matrix cos theta sin theta minus sin theta cos theta, then An equal to matrix cos n theta sin n theta minus sin n theta cos n theta. Solution. We have Pn An equal to matrix cos n theta sin n theta minus sin n theta cos n theta. We note that P1 equal to A1 equal to matrix cos theta sin theta minus sin theta cos theta. Therefore, P1 is true. Assume that Pk is true, that is Pk that is AK equal to cos matrix cos k theta sin k theta minus sin k theta cos k theta. We want to prove that P of k plus 1 is true whenever Pk is true, that is Pk plus 1, that is A k plus 1 equal to cos k plus 1 theta matrix cos k plus 1 theta sin k plus 1 theta minus sin k plus 1 theta cos k plus 1 theta. Now A k plus 1 equal to Ak into A. Since Pk is true, we have A k plus 1 equal to matrix cos k theta sin k theta minus sin k theta cos k theta into cos theta matrix cos theta sin theta minus sin theta cos theta equal to, by matrix multiplication, matrix cos k theta minus sin k theta sin theta cos k theta sin theta plus sin k theta cos theta minus sin k theta cos theta minus cos k theta sin theta minus k theta sin theta plus cos k theta cos theta equal to matrix cos of k plus 1 theta sin k plus 1 theta minus sin k plus 1 theta cos k plus 1 theta. Thus Pk plus 1 is true whenever Pk is true. Hence Pn is true for all n greater than equal to 1 by the principle of mathematical induction. 3. Prove by cases or by exertion. The method of proving a statement P implies Q is possible only when P can be split into several cases R, S, T, say, so that P equal to R or S or T, where the sign V is the symbol for OR. If the conditional R implies Q, S implies Q, and T implies Q are proved, then R or S or T implies Q is proved, and so P implies Q is proved. The method consists of examining every possible case of hypothesis. It is practically convenient only when the number of possible cases are few. Example 4. So that in any triangle ABC, A equal to B cos C plus C cos B. Solution. Let P be the statement ABC is an triangle and Q be the statement A equal to B cos C plus C cos B. Let ABC be a triangle. From A, draw ADA perpendicular to BC. BC produced if necessary. As we know that any triangle has to be either acute or obtuse or right angle, we can split P into three statements R, S and T, where R means ABC is an acute angle triangle with angle C is acute. S, that is ABC, is an obtuse angle triangle with angle C is obtuse. T, that is ABC, is right angle triangle with angle C is right angle. Hence we prove the theorem by three cases. Case 1. When angle C is acute from the right angle triangle ADB, that is BD by AB equal to cos B, BD equal to AB cos B equal to C cos B. ABC triangle, AD is perpendicular, AB is called C, AC is called B and BC is called A. ADB angle is a 90 degree. From the right angle triangle ADC, CD by AC equal to cos C, that is CD equal to AC cos C equal to B cos C. Now A equal to BD plus CD equal to C cos B plus B cos C dot dot 1. Case 2, when angle C is obtuse, figure A 1.2, from the right angle triangle ADB, BD by AB equal to cos B. BD equal to AB cos B equal to, that is C cos B. ABC is a triangle, AC is called B, AB is called C, and BC is called A. And AD or CD is obtuse. From the right angle triangle ADC, CD by AC equal to cos angle ACD. Cos 180 degree minus C equal to minus cos C. That is CD equal to minus AC cos C equal to minus B cos C. Now A equal to BC equal to BD minus CD, that is A equal to C cos B minus of minus B cos C. A equal to C cos B plus B cos C dot dot 2. Case 3, when angle C is right angle, figure A13, ABC triangle AB is C, AC is B, and BC is A, and ACB angle is 90 degree. From the right angle triangle ACB, BC by AB equal to cos B, that is BC equal to AB cos B, A equal to C cos B, and B cos C equal to B cos 90 degree equal to 0. Thus we may write A equal to 0 plus C cos B equal to B cos C plus C cos B dot dot 3. From 1, 2 and 3 we assert that for any triangle ABC, A equal to B cos C plus C cos B. By case 1, R implies Q is proved. By case 2, S implies Q is proved. By case 3, T implies Q is proved. Hence, from the proof by cases, R or S or T implies Q is proved, that is P implies Q is proved. Indirect proof. Instead of proving the given proposition directly, we establish the proof of the proposition through proving a proposition which is equivalent to the given proposition. 1. Proof by contradiction, means reductio ad absurdum. Here we start with the assumption that the given statement is false. By rules of logic we arrive at a conclusion contradicting the assumption, and hence it is inferred that the assumption is wrong, and hence the given statement is true. Let us illustrate this method by an example. Example 5, show that the set of all prime numbers is infinite. Solution. Let P be the set of all prime numbers. We take the negation of the statement the set of all prime numbers is infinite, that is we assume the set of all prime numbers to be finite. Hence we can list all the prime numbers as P1, P2, P3 dot dot Pk. Say, note that we have assumed that there is no prime number other than P1, P2, P3 dot dot Pk. Now consider n equal to P1, P2, P3 dot dot Pk plus 1 dot dot 1. N is not the list as n is larger than any of the numbers in the list. N is either prime or composite. If n is prime, then by 1 there exists a prime number which is not listed. On the other hand, if n is composite, it should have a prime divisor, but none of the numbers in the list can divide n. because they all leave the remainder 1. Hence, the prime divisor should be other than the one in the list. Thus, in both the cases, whenever n is a prime or a composite, we ended up with contradiction to the fact that we have listed all the prime numbers. Hence, our assumption that set of all prime numbers is finite is false. Thus, the set of all prime numbers is infinite. Note, observe that the above proof also uses the method of proof by cases. 2. Proof by using contrapositive statement of the given statement. Instead of proving the conditional P implies Q, we prove its equivalent, that is, implies Q implies P. Students can verify the contrapositive of a conditional can be formed by interchanging the conclusion and the hypothesis and negative both. Example 6. Prove that the function f, that is r to r, defined by fx equal to 2x plus 5 is 1 1. Solution: a function is 1 1 if fx1 equal to fx2 and implies x1 equal to x2. Using this, we have to show that 2x1 plus 5 equal to 2x2 plus 5 implies x1 equal to x2. This is of the form P implies Q, where P is 2x1 plus 5 equal to 2x2 plus 5 and Q, that is x1 equal to x2. We have proved this in example 2 of direct method. We can now prove the same by using contrapositive of the statement. Now, contrapositive of the statement is implies Q implies P, that is contrapositive of if fx1 equal to fx2, then x1 equal to x2. If x1 not equal to x2, then fx1 not equal to fx2. Now, x1 not equal to x2 implies that 2x1 not equal to 2x2, implies that 2x1 plus 5 not equal to 2x2 plus 5, implies that fx1 not equal to fx2. Since implies Q implies P is equivalent to P implies Q, the proof is complete. Example 7 shows that if a matrix A is invertible, then A is non-singular. Solution: writing the above statement in symbolic form, we have P implies Q, where P is matrix A is invertible and Q is A is non-singular. Instead of proving the given statement, we prove its contrapositive statement, that is, if A is not a non-singular matrix, then the matrix A is not invertible. If A is not a non-singular matrix, then it means the matrix A is singular, that is, A not equal to mod of A equal to 0. Then A inverse equal to adjacent A by mod of A does not exist as mod of A equal to 0. Hence, A is not invertible. Thus, we have proved that if A is not a non-singular matrix, then A is not invertible. That is, not Q implies not P. Hence, if a matrix A is invertible, then A is non-singular. 3. Prove by a counter example. In the history of mathematics, there are occasions when all attempts to find a valid proof of a statement fail and the uncertainty of the truth value of the statement remains unresolved. In such a situation, it is beneficial if we find an example to falsify the statement. The example to disprove the statement is called a counter example. Since the disproof of a proposition P implies Q is merely a proof of the proposition, not of P implies Q, hence this is also a method of proof. Example 8, for each n, 2 to the power 2n plus 1 is a prime, n belongs to n. This was once thought to be true on the basis that 2 to the power 2 1 plus 1 equal to 2 to the power 2 plus 1 equal to 5 is a prime. 2 to the power 2 of 2 plus 1 equal to 2 to the power 4 plus 1 equal to 17 is a prime. 2 to the power 2 of 3 plus 1 equal to 2 to the power 8 plus 1 equal to 257 is a prime. However, at first sight, the generalization looks to be correct, but eventually it was shown that 2 to the power 2 to the power 5 plus 1 equal to 2 to the power 32 plus 1 equal to 4294967297, which is not a prime since 4294967297 640 equal to 641 into 6700417, a product of two numbers. So the generalization for each n 2 to the power 2 to the power n plus 1 is a prime, that is n belongs to n, is false. Just this one example 2 to the power 2 to the power 5 plus 1 is sufficient to disprove the generalization. This is the counter example. Thus we have proved that the generalization for n 2 to the power n plus 1 is a prime, n belongs to n is not true in general. Example 9, every continuous function is a differentiable. Proof. We consider some function given by 1 fx equal to x square, gx equal to e to the power x, 3 hx equal to sin x. These functions are continuous for all values of x. If we check for their differentiability, we find that they are all differentiable for all the values of x. This makes us to believe that the generalization every continuous function is differentiable may be true. But if we check the differentiability of the function given by phi x equal to mod of x, which is continuous, we find that it is not differentiable at x is equal to 0. This means that the statement every continuous function is differentiable is false. In general, just this one function phi x equal to mod of x is sufficient to disprove the statement. Hence, phi x equal to mod of x is called a counterexample to disprove every continuous function is differentiable.